Welcome to this scientific lecture on how Newton and other scientists discovered the law of universal gravitation. This is one of the most remarkable stories in the history of physics. To understand Newton's achievement, we need to go back to the early 1600s. Before Newton, astronomers had accumulated vast amounts of data about planetary motion, but they didn't have a fundamental physical law that explained why planets moved the way they did. Johannes Kepler had already formulated 3 laws that described how planets moved. These were empirical laws, meaning they were based on observations, but they didn't explain the underlying cause. Kepler's laws told us what planets did, but not why they did it. This is a crucial distinction in physics. Describing motion is one thing, understanding the forces that cause motion is another. Let's quickly review Kepler's 3 laws because they were essential to Newton's discovery. Kepler's first law states that planets move in elliptical orbits with the Sun at one of the 2 foci. This was revolutionary because everyone before Kepler thought orbits had to be perfect circles. Here's an ellipse representing a planetary orbit. The Sun sits at one focus, not at the center. The planet traces this elliptical path as it orbits. Kepler's second law states that a line connecting the planet to the Sun sweeps out equal areas in equal time intervals. This means planets move faster when closer to the Sun and slower when farther away. Kepler's third law relates the orbital period to the size of the orbit. Specifically, the square of the orbital period is proportional to the cube of the semi-major axis. Mathematically, t squared is proportional to a cubed, where t is the period and a is the semi-major axis of the ellipse. Now here's an important question. How did Newton use Kepler's laws to discover the law of universal gravitation? The answer involves a brilliant combination of mathematics, physics, intuition, and careful analysis of data. Newton started by simplifying the problem. Instead of dealing with ellipses right away, he first considered circular orbits. This is a common scientific strategy. Solve the simpler case first, then generalize. For an object moving in a circle at constant speed, the acceleration must point toward the center. This is called centripetal acceleration. The magnitude of centripetal acceleration equals v squared over r, where v is the orbital speed and r is the radius. The orbital speed can be expressed in terms of the period t and radius r. The planet travels a distance of 2 pi r in time t. So versus equals 2 pi r over t. Now comes the clever part. Newton substituted this expression for versus into the centripetal acceleration formula. When we substitute versus equals 2 pi r over t into a equals versus squared over r, we get 4 pi squared r over t squared. But from Kepler's third law, we know that t squared is proportional to r cubed. Let's write this as t squared equals k times r cubed, where k is some constant. Substituting t squared equals kr cubed into our acceleration formula, we get a equals 4 pi squared over kr squared. Notice what happened. The acceleration is inversely proportional to r squared. This is the crucial discovery. The centripetal acceleration required to keep a planet in orbit decreases as 1 over r squared. This is the inverse square law. Acceleration is proportional to 1 over r squared. By Newton's second law, F equals ma, the force must also be inversely proportional to r squared. This is the gravitational force law. The gravitational force from the Sun spreads out in all directions. As you move farther away, the force weakens according to the inverse square law. You might ask, why does the force fall off as 1 over r squared? Why not 1 over r or 1 over r cubed? This is a deep question. There's a beautiful geometric reason. Imagine the gravitational influence spreading outward from the Sun. At distance r, this influence is spread over the surface of a sphere of radius r. The surface area of a sphere is 4 pi r squared, so if the total gravitational influence is constant, the force per unit area must decrease as 1 over r squared. Now Newton had a mathematical model, force proportional to 1 over r squared, but how did he know this was correct? He compared predictions with the best observational data available. Tycho Brahe, working before the telescope was invented, had compiled amazingly precise measurements of planetary positions over many years. Kepler used this data to formulate his laws. With his inverse square law, Newton could mathematically calculate what the orbit should look like and compare them to the observed orbits in Tycho's data. One of Newton's most famous tests was comparing the force that keeps the moon in orbit with the force that causes objects to fall on Earth. The moon orbits at a distance of about 60 Earth radii from the center of the Earth. If the inverse square law is correct, the gravitational acceleration at the moon's distance should be 60 squared, or 3,600 times weaker than at Earth's surface. The ratio of accelerations should be 1 over 3,600. At Earth's surface, we know the gravitational acceleration is 9.8 meters per second squared. So at the moon's distance, the acceleration should be about 0.0027 meters per second squared. Now we can independently calculate the moon's centripetal acceleration from its orbital motion. Using A equals 4 pi squared r over t squared, where r is the moon's orbital radius, and t is its period of 27.3 days. When Newton plugged in the numbers, he got approximately 0.0027 meters per second squared. The inverse square law prediction matched the observed acceleration perfectly. This agreement was remarkable. It showed that the same force that makes apples fall on Earth also keeps the moon in its orbit, weakened by the inverse square of distance. This was a profound unification. Now we come to a deep philosophical question about science. How do we turn a mathematical curve that fits data into a general physical law? This is not trivial. The first step is pattern recognition. Newton found that planetary data followed an inverse square pattern. But fitting data is not enough. The second step is to test the pattern in as many different situations as possible. Newton tested it with the moon, with planets, with Jupiter's moons, with comets. The third step is to connect your pattern to fundamental principles. Newton's second law, F equals ma, provided the connection between the acceleration pattern and force. The fourth step is to make predictions that go beyond the original data. Newton predicted comet orbits, tides, the shape of Earth, and perturbations in planetary motion. Let's look at a concrete example of Newton's predictions. Edmund Halley, Newton's friend, used the law of gravitation to predict the return of a comet. Halley noticed that comets had appeared in 1531, 1607, and 1682, roughly 76 years apart. He hypothesized these were the same comet returning. Using Newton's gravitational law, he calculated the orbit and predicted the comet would return in 1758. This was a bold prediction, because Halley knew he wouldn't live to see it. On Christmas Day 1758, the comet appeared exactly as predicted. This was stunning confirmation that Newton's law was not just curve-fitting, but a true law of nature. Now let's write down the final form of Newton's law of universal gravitation in all its glory. The gravitational force between two masses m1 and m2 separated by distance r is g times m1 times m2 divided by r squared. G is the universal gravitational constant. Its value is approximately 6.67 times 10 to the negative 11 in SI units. This constant was measured by Cavendish in 1798, more than 70 years after Newton's death. The force is always attractive. Pulling the masses together, it acts along the straight line connecting the centers of the two masses. The truly remarkable thing is that this same law applies to all masses everywhere. From the smallest pebble to the largest galaxy, from here on Earth to the farthest reaches of the cosmos. This brings us to an important question. What makes Newton's equation a law of nature rather than just a mathematical formula? This is about the philosophy of physics. A physical law must be universal, applying everywhere and at all times. It must be predictive, allowing us to calculate outcomes before observing them. And it must be falsifiable, meaning we could prove it wrong if it didn't match observations. Newton's law of gravitation satisfies all three criteria. It applies throughout the universe, it makes precise predictions, and it could have been falsified if observations didn't match. Let me give you a practical example of using Newton's law. We can actually calculate the mass of the Earth using gravity. We know that at Earth's surface, objects accelerate downward at 9.8 meters per second squared. By Newton's law, this acceleration g equals g times the mass of Earth divided by Earth's radius squared. Solving for Earth's mass, we get m sub e equals g times r sub e squared divided by g. Earth's radius is approximately 6.37 times 10 to the 6 meters. Plugging in the numbers, we get Earth's mass is approximately 5.97 times 10 to the 24 kilograms. That's how we weigh the Earth. It's important to note that Newton's law, while incredibly successful, is not the final word. Einstein showed that Newton's law is an approximation. For everyday situations, weak gravitational fields, and speeds much less than the speed of light, Newton's law is essentially exact. But near black holes, near neutron stars, or for objects moving at speeds close to light speed, Newton's law breaks down and we need Einstein's general relativity. Even in our solar system, Mercury's orbit showed a tiny discrepancy that Newton's law couldn't explain. Einstein's theory explained it perfectly. Let's summarize what we've learned about how science progresses from observations to laws. First, collect precise observational data. Tycho Brahe spent decades measuring planetary positions with unprecedented accuracy. Second, identify mathematical patterns. Kepler found that orbits are ellipses and discovered his 3 laws relating periods and distances. Third, propose a physical mechanism or force law that explains the patterns. Newton proposed the inverse square law of gravitation. Fourth, make predictions and test them against new observations. Newton tested his law with the moon, comets, and tides. Fifth, be willing to refine or replace the law if new observations don't match. This is what happened when Einstein improved on Newton. Let me leave you with the key takeaways from this lecture. The inverse square law of gravitation emerged when Newton combined Kepler's third law with the mathematics of circular motion. What transformed this from curve fitting to a physical law was extensive testing against diverse phenomena: planetary orbits, the moon, comets, and tides. A true physical law must be universal in scope, predictive of new phenomena, and falsifiable by observation. Even Newton's magnificent law turned out to be an approximation of Einstein's deeper theory, reminding us that science is always provisional and open to refinement. Finally, understanding how Newton discovered his law teaches us as much as the law it's. The scientific method of observation, pattern finding, hypothesis, prediction, and testing is the foundation of all scientific progress.